Hi everyone, I'm Tobias. I'm an undergraduate at TUM, and I'll talk a bit about my work on formal verification of polynomial commitment schemes, specifically the KZG. This work is in Isabel. I kind of prepared this presentation before I knew how big the Ethereum Foundation formalization in Lean was. So I'll talk about this a bit in the end, but just keep that in mind. To kind of see where this work lies in the realm of formal verification, I illustrated a little picture. I call it the Tower of Formal Verification. So here on top you have the paper proofs. So these are the first formal proof by hands, just the proofs you're used to from reading the papers. And then second instance, formal verification of these proofs. So in a theorem prover like Lean or Isabel. So these are the machine-checked proofs. And then kind of as a last instance, formal verification of implementations, where I mean with formal verification of implementations, more that the source code is proven equivalent to a certain specification. And this talk will be solely about the second layer, so formal verification of cryptographic proofs. And the rest of this talk will basically split up into two parts. The first one will be about the about the formal verification tool I used and formal verification methodology in general. And then the second one will be about the actual contents of this work. The motivation behind this is to kind of show you what is the soundness of these proofs and the quality, but also the limitations, of course. So let's get right into it. So I used cryptol. Cryptol is a framework specifically designed for cryptographic proofs in Isabel. Isabel is a proof assistant. If you know it, if you don't know it, it's like Coq or Lean. So essentially, how it works is it's based on higher order logic in Isabel's case. So you have a small verifier that essentially checks these higher order logic statements, and then on top of that, you have more complex and better user-friendlier frameworks like Crypto, for example. In Isabel's case, this verifier kernel is written in standard ML, which is a very strongly typed language, and it's been used for decades at this point. So really, this is as good as you can get, I think, for tools like this. So essentially minimal assumptions for maximal security. So then about Cryptol. So how does Cryptol work? On a high level, Cryptol follows the sequence of games approach. I'm sure most of you are somewhat familiar with that. Still, for those who don't, I'll go quickly over it. The basic assumption is you have these games as probability spaces, and then you define this sequence of games, starting with game 1, then game 2, and so on, till game n. Game 1 is typically your attack game, game n, your hardness assumption game. And then what you do, you hop from one game to the next, every time proving that the difference between winning the first game is negligible due to the winning the second game, like I and I plus 1, I guess. And how do these game hops look like? I want to talk about two specific game hops. The first one being the bridging step. So this is essentially just restating your game. Here I swapped A and A prime. I mean, this can be more complex and more complex games, of course. And the second one is the game hop based on a failure event. So essentially you have two games that behave the same, except for a certain event, this failure event, which of course can only or should only occur with a negligible probability. So these two games differ only with negligible, like the difference between those games is only negligible. In this example game, we obviously see that on the right-hand side, if we sample A as 0, which I include because we're computer scientists, then you're going to have a hard time on the right-hand side, while the left-hand side has still some probability to win. So in that case, these two differ, but in every other case, these two should be relatively the same. So why am I talking about these two game hops specifically? So these are specifically optimized in Isabel. So like I said, Isabel is general purpose, like Lean, so you can do essentially any kind of game hop. But there's really great tooling for these two. And in my formalization and formal verification of the KZG, I used only these two, and you really can go a long way with these two. Right. So let's take a look at how these games look in Isabel. So here's an example. this is the same game on the left-hand side in Isabelle, of course. And yeah, as you can say, these look roughly the same. I mean, on the left-hand side, we have this try do else block, but other than that, that should look fairly similar. So yeah, formally, these games in Isabelles are monads over subprobability mass functions. If you don't really know what that is, don't worry, you can just see it's basically the same. And this try to else block, the purpose of that is basically to accommodate for the subprobability mass function, namely to capture the case of non-termination, or if something goes wrong, like the division by 0 in the last game. And yeah, essentially for this sequence of games proofs, we define these games in Isabelle, and then we justify each game hop with theorems in Isabelle. So I brought a little example. Don't be shocked now, it might look a bit much, but yeah, don't worry. The important part is, I have something like this, right? So you see we have these try do else blocks here again, right? So these are all single games, so we have 4 games. And then we have these also half blocks, right? And these also half blocks, they're always statements we want to prove. So we also always have point should be equal to this new game. So essentially a bridging step. And these 3 points, they always refer to the game above. So these 3 points refer to that game. And right below, we always have this justification in Isabelle. Here it is by simp add, and then we have some facts. And these facts are basically setting the equivalence for the bridging step. So here's one cute example below. So we have here the one-time pad, and we see here in this game we have C as a uniformly randomly sampled value, and then in the game above we see, okay, there's something complicated going on. Now, this is some Isabelle stuff with the map SPMF and the lambdas and some functional programming, but essentially it's just adding either M0 or M1 to a uniform random value. And obviously we can use a one-time pad to make it a bit easier. Yeah, this is a real-world example. So this is not from my proofs because, polynomial commitment scheme games are a bit larger, so that will not fit quite on the page. But these are from Peterson commitments from the hiding proof. So yeah, but the really nice thing about this kind of proving is that essentially if you trust Isabelle, you can say, okay, so these steps, they're all correct. So the only thing I need to do is to verify the first game and the last game. So this is quite convenient because the first game we always said is the attack game and the last game is the hardness assumption game. So essentially, I don't have to worry about these map SPMF stuff and weird Isabelle stuff. I can just look at the playing games that should look almost the same as the games you know and love. So yeah, to sum it up, in Cryptol and Isabelle, we have this very small verifier, so we are basically as secure as it gets. We have the sequence of game style proof, so we really only need to audit the first game and the last game, so the hardness assumption game and the attack game. Which makes auditability of these proofs basically a thing of minutes. And we have these games as monads, at least for the attack game and the hardness assumption game. These should also be very easily auditable for non-formal verification or Isabelle experts, so just your regular cryptographer. Right, so that's it about the Cryptol part. Now let's get to the contents of this work, like the work I actually did, and that is, firstly I formalized an abstract polynomial commitment scheme in Isabelle, including all the security games you have, like polynomial binding, evaluation binding, hiding, knowledge soundness, correctness, just your usual stuff. And then I instantiated this abstract polynomial commitment scheme with the standard KZG. Proved basically everything that's possible, so virtually everything except hiding. And then to kind of show the versatility of this definition, I also formalized a batched version of the KZG, so the one where you're batching evaluations. We'll get a bit more to that later. And of course, also proved all possible security properties for that. And to go one step further, I also proved a property called weak hiding for the standard KZG. I'll get to that in the next slide, one of the next slides. Yeah, and to kind of really sum it up, we all know the KZG knowledge sound is usually proven in the AGM. I mock that in my proofs now, but yeah, I currently am formalizing that properly in Isabelle. Yeah, so let's take a look at how it looks. Concretely in Isabelle, we have this abstract polynomial commitment scheme defined as a locale. A locale in Isabelle is comparable to a trait in Rust, or I think it's interface in Java. So really, we assume we have these few functions, just the standard polynomial commitment scheme functions, and then we can yeah, do stuff with them, define games, for example. Like I said, I defined all the standard security games. So here's one example of the evaluation binding game. So there is some more Isabelle stuff, like where this is actually a function, and we take an evaluation binding adversary, and we get a Boolean SPMF. Yeah, this Boolean SPMF is basically capturing if the adversary has won the game or not. And yeah, I think this part here is probably most important for you, and I think it should look fairly yeah, familiar. And then additional to defining the games, we also, or I do also define the advantages for the adversary. So I do not define concrete security statements like, I don't know, statistical binding, computational hiding, and so on. I leave that to the concrete instantiations, but basically give the instantiators all the tools they need at hand, namely the advantage of the adversary. Yeah, that's basically their only task to reduce that and say, okay, that is 0 or negligible. Yeah, now let's take a look at the the actual work I did. So like I said, the standard KZG, these are all the properties I proved. So I will not go into the proofs because I think that's probably yeah, a bit too much. But about the weak hiding point, so we all know the standard KZG is not hiding, but in fact it is hiding for uniformly random polynomials. Yeah, how sensible that is, okay. But yeah, there's actually this nice thing we can do in Isabelle. So like I said, games are functions, and in Isabelle, if you want to prove a statement about a function and you have uninitialized parameters, these are assumed to be arbitrary, so you have no assumptions whatsoever. So we can very easily make games more strict by just initializing these parameters. So for the hiding game, we can just initialize the polynomial to be uniformly random, and just like that, we don't have the possibility of error in somehow mingling with the hiding game. We can just use the formalized one, and yeah, this property was yeah, it was a bit hard to formalize, but it's another story. Yeah. On top of that, the batch KZG, yeah, basically prove all the same properties, so completeness, binding, evaluation binding, and knowledge soundness. The weak hiding proof is another thing. I didn't do that. Yeah, we can talk afterwards if you're interested in that. So yeah, it's basically, like I said, it's evaluation batching. So it's not a typical Planck-like batching where you take multiple polynomials and evaluate them in a batch, but it's rather batching the multiple evaluations of one polynomial. So just to be clear about that. All right, so now, oh yeah, sorry, forgot a little anecdote. So I don't know if you ever checked out like the KZG paper, and be it the ePrint version or AsiaCrypt. I mean, try it and try to look for the proofs. They won't be there. They're only on an extended version that is somewhere on some Waterloo server. So yeah, if you have never gone that far, yeah, I guess you don't have to anymore, except for educational purposes, of course. Right, now to the AGM. So since it's a cryptography event, I'm going to spare you all the functional programming, magic, and monads and functors and so on. But basically, the random oracle model is already formalized in Isabelle, and they did a really nice thing where they have you can see it as a compiler from types. So all the games I defined are in the standard model, but you can very easily in Isabelle port them to the random oracle model with this new type. Then yeah, has access to oracle, shared oracle, and you can log the oracle queries and so on. And basically, we're doing something similar for the AGM, so logging group elements. But yeah, that is work in progress. Yeah, I cannot tell you too much about that. Yeah, I think that's it about the AGM. So we all know polynomial commitment schemes are interesting on their own, but of course they are even more interesting in the context of more primitives and even complexity theory. And that's why I wanted to show you a little, I call it ZK Isabel. I mean, of course, it's kind of an ecosystem for snarks more than in ZK, but yeah, here are a few things that are already formalized in Isabel. So we have the sum check protocol, we have the random oracle model, we have Peterson commitments, and a few other commitment schemes. We have the Sigma protocols, and we have really an extensive array of algebra and number theory. And well, polynomial commitment schemes are only the latest addition to that. Of course, there's like one big thing missing to kind of bring this thing home, and that would be IOPs and Fiat-Shamir, which kind of brings me to the future work. So obviously, if you have IOPs and Fiat-Shamir, you can formalize all kinds of polynomial commitment schemes, like error-correcting code base like Fry, Were, Binias, Stir, basically all the work that got me excited last year at ZKP6 and this year again. And also interactive based multilinear polynomial commitment schemes like Zeromorph and the one used in Halo. And of course, the biggest name, Snarks. And with this extensive, or I don't want to say extensive, but with this array of primitives already formalized, we can not only formalize, I say, basic Snarks like Plonk, but also, I mean, more advanced ones, folding schemes, for example. But yeah, the main disadvantage we have in Isabel is, I mean, we don't really have that big of a funding as Lean with the Ethereum Foundation has. And also these formalizations, every one of them is kind of singly handled, step by step, so to say. And I mean, I really like the approach of the Ethereum Foundation, doing it all in a modular way, co-designing everything, doing a library. So I want to actually scrap what I said last, and yeah, just do it in Lean. I guess this yeah, I guess it's kind of obsolete, but yeah. And I think yeah, just to have a little summary. So what did we do concretely in this work? We formalized an abstract polynomial commitment scheme in Isabel. We instantiated 2 concrete KZG versions and transformed the paper proofs into more rigorous sequence of game style proofs. Yeah, we formalized these proofs and currently are formalizing the AGM in Isabel. Yeah, next stops IOPs. I guess that's really then. Yeah, that's it about it. You can find the paper I submitted here and the GitHub code on my website, which I actually just created for this like a week ago. And yeah, I'm happy to discuss afterwards. This was the meme I wanted to share, but I guess it's more like this now. Okay, thank you.
So you said that because your formalization of the AGM wasn't available, you mocked that out in the proof for PCSs. How does that work? Say more about that.
I mean, essentially, you have to twinkle a bit with the types, right? So now you the adversary type, you basically add types to also send you the vectors. And then you put some asserts under that and saying, okay, this vector is actually the group value. So yeah, it's pretty ugly. So yeah.
Thank you.
Any questions?
Yeah. So.
Oh yeah.
You said, of course, the thing you have to verify is the first statement and the last statement. Do you have in your slides any example of like the algebraic assumption that, for example, that you use to prove binding or hiding or anything like that? What's your end statement? It has to be some cryptographic.
Yeah. So I mean, yeah, good point. I should have probably put that on the slides. I only have an attack game, but like similar to the attack game, you can also define a game for a discrete log or something like that, and or TSDH in the case of Isabel should look fairly similar. I can show you afterwards if you want to see it.
QSDH has this parameter where you get Q of these things, right? So you were able to model that?
Yeah, sure. I mean, like I said, these games are always like kind of functions. So essentially, what you do is you provide another argument to the function, namely how many of these instances you want to have, and that's how it works.
Thanks. This is really nice work. You're building on the PhD thesis of David Butler, doing
Yep.
the commitment schemes and the Sigma protocols. We already ported that to SS Proof, so in ROC it's also available. So that would be a lot faster to port. And I also recommend everyone to look at that work in other provers, because it really helps to do your formalization, even though the details are different.
Thank you.
Anyone else?
So I have one quick question. I haven't done anything in Isabel. I think last time I did things in Isabel was 2016. How did you find working with the AFP, and was there any kind of thing missing there?
I mean, working with the AFP is fairly easy. So I think that wasn't the hard part. But of course, there were some hard parts with, for example, there was no formalization of pairing, so you kind of have to do assumptions about that, and preparing everything about that around that was a bit of a pain.
Yeah, we're missing pairings in Lean as well, so I was curious about that specifically.
Okay.
Can you explain the AFP?
AFP is the archive of form proofs in Isabel, which is somewhat dissimilar to like masscomp in RONC or masslib in Lean, in the sense that it's a bit more like a collection of papers than a kind of nice, software library. And it's a bit chaotic sometimes as a result.
Yeah, but at least from my experience, it's defined very modular. You always have these abstract schemes, and I mean, you can. I even used it in the abstract polynomial commitment schemes for the normal binding, so polynomial binding.
Fantastic. Anything else?
Okay, thank you everyone. And we're gonna have a coffee break, but before we have the coffee break and fill our bellies with a lot of butter, we're gonna take a group photo of everybody, and we're gonna take it in the stairs leading to the lobby. So if you guys can go there before you take a croissant,